Hello everybody, Mr. C here. I just wanted to make a video going through example 7 on your note sheets for the related rates notes because we didn't get to it in class. We did number 6, which had the same setup, but let's do a quick review of that setup. So number 7 says, a camera is placed 3,000 feet from a rocket launching pad. If a rocket is rising vertically at 880 feet per second when it is 4,000 feet in the air, how fast must the elevation angle change at that instant to keep the rocket in sight? Let's draw it. So I have a camera right there, and there's a rocket. And the rocket starts on the ground. And they were how far apart? They were placed 3,000 feet apart. Okay. The rocket's going to take off, but it's going vertically, right? So this 3,000 feet, no matter how high the rocket goes, the distance from the camera to where the rocket started isn't going to change. All right, so let's now imagine that the rocket is taken off. Oh, that's not what I meant to do. There we go. And now we're at 4,000 feet in the air. So we have this nice triangle. It's a right triangle because it goes vertically upwards. And the rocket is increasing at 880 feet per second when it's 4,000 feet in the air. Okay, but the rocket's not always 4,000 feet in the air, right? This distance from the ground where the rocket started to however high it goes is changing over time. So we can't just write 4,000 here on this side of the triangle. We need a variable. Let's use A. Okay. Now, we're trying to find the elevation angle's change, or rate of change. The elevation angle refers to this angle here, right? You can think about this to be this angle and not this one, because this one, you know, as the rocket goes up, 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 this, you can imagine it'll be something like this. So we'll have this angle here kind of measures how high it's going in a sense. Okay, so let's translate the problem into math notation to make our lives a little easier. So the question is asking, if the rocket is rising vertically at 880 feet per second when it is 4,000 feet in the air, okay, we've named that this height is A. So when A is 4,000 feet and dA dt is 880 feet per second, right? This is dA dt because it's the rate of change over time that A is changing. Find the rate of change of the elevation angle. All right, so let's name the elevation angle. Let's use theta. And we want the rate of change of theta with respect to time, so that's d theta dt. All right. So at some point, right, at the point we care about, we know what this side of the triangle is. It's 4,000. And this one's always going to be 3,000. And we're trying to find theta, so we can relate the angle here to a trig function. And if you remember SOHCAHTOA, we're going to want to use TOA, right? The tangent of this angle is the opposite side divided by the adjacent side, OA. So tangent of theta equals A over 3,000. Right? The reason we get this, or we want this, is because this is the way that we can relate that angle, theta, to the information that we know, right? We know A only at one place, but that's okay. And we always know what this side is. So really the first part of this is just getting an expression that includes what we know and the variable we want to eventually get the derivative of. From here, if we differentiate both sides, okay, well, the derivative of tangent theta is secant squared theta, but we want with respect to time, not theta, so we need our d theta dt term here, and that's because of the chain rule. Similarly over here, well, this is just a constant multiple of 1 over 3,000, and then dA dt, because we want the rate of change of A. All right, and we're trying to find d theta dt, so we need to solve for it. And we do that by dividing both sides by secant squared theta. So we're left with something that looks like this, dA dt divided by 3,000 times secant squared theta. Okay, can we solve this right now? Can we solve for d theta dt? Well, not quite. At the moment we are concerned with, right, which is when A is 4,000 feet, we know that dA dt is 880 feet per second. Good, we need dA dt for that expression we just found, or equation we just found. But we also need to know what theta is at that moment. So we actually need to solve for theta when A is 4,000 feet. We can do that using this same equation before we differentiate it. So tangent of theta is, well, we know that's going to be 3,000, and we care about what theta is when A is 4,000. So we plug in 4,000 here. All those zeros cancel out, so we're left with tangent of theta is 4/3. And nice trig review. If we want to get theta by itself, we need to do the inverse trig function to both sides. The inverse trig function, inverse tangent, is just the inverse function of the tangent function. So like any time we do an inverse of an operation, like multiply a number by 2 and then divide by 2, they just cancel out and we're left with theta, which is why we did this in the first place. All right. So we have theta by itself and we have, a function of a number. So we're good. We've found theta. And now we can plug it in here. We can also plug in our dA dt. So d theta dt is equal to, dA dt was 880 feet per second. And then we have 3,000 on the bottom times secant squared of our theta, which is the inverse tangent of 4/3. All right, so we're not quite done, right? This is a pretty ugly expression. If this were no calculator, you would be able to leave this number as is, right? We don't have any variables on the right-hand side of this equation, so we're good. We've solved for it, but we can use a calculator for this assignment, so let's do that. And we should probably talk about how to put this in the calculator because it's not super obvious. If you want to put this in the calculator, you need to there's no secant button on the calculator. So if you need to put this in the calculator, you do 880 divided by 3000 times one of the trig functions that is on the calculator, which is, well, cosine is related to secant by a relationship of 1 divided by cosine. So let me write that down. That wasn't very clear. Secant of theta, whatever theta is 1 over cosine of theta. That's just a trig identity. What that means is secant squared of theta, right? If we square this side, we can square this side. We get 1 over cosine squared of theta. So here, to put it in the calculator, make sure to put parentheses. We have 1 divided by cosine squared of the inverse tangent of 4/3, all in parentheses, like that. One final note. Make sure you're in radian mode on your calculator. Now, personally, when I'm doing these kinds of equations, I don't like to keep the units in. You can, but I don't like to. I like to first determine what my units should be, right? I'm looking for a rate of change of theta with respect to time. So radians per second or degrees per second. In this case, it would be radians because we're using radians. But if you want to put your units in, we know this is unitless. Secant squared of this angle is unitless. And we had 3000 feet times all this unitless stuff. So the feet and the feet are going to cancel out, and we get units of 1 over seconds. But wait, I said that this was in radians per second. Well, remember, radians are effectively unitless. All right, last thing we got to do is to write this in terms of the problem. Oh, and let me give you the decimal approximation. So d theta dt is about, where did I put it? 0.1056, blah, 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 radians per second. Which we can round to 0.106 rad per second. All right, so let's take a look at the problem again. We were trying to find how fast the elevation angle changes at the instant when the rocket is 4,000 feet in the air. So when the rocket is 4,000 feet in the air, the elevation angle is, all right, this was a positive number, so it's increasing at a rate of 0.106 rads per second. And we'll say about, because we rounded. Okay, this was not an easy problem. We had a really complicated mess here. During next week's async, please let me know if you'd like me to go over this further. I would be happy to. You will have access to this document with all this work on it, and I'll post the video today. All right, thanks for tuning in.